Now I'm going to talk about a work we are working on called mRPC. Our goal is to build a new RPC system so that it is better to work with a service mesh. So this work is a joint work with Duke University, University of Washington, and Shanghai Jiaotong University. So RPCs are widely used. I don't need to repeat that. It is used in a lot of different applications. And for RPCs, the performance actually matter a lot. I mean, the data plane performance in Google's data center RPCs generate 90% of the application traffic, and the Google data center spends around 10% of its CPU cycles on RPC processing. And the performance is always the key design goal for an RPC library or RPC system. Now, what is an RPC? So to implement an application using RPC, first you need to define some protocol specification, and you can call it a protofile. Then you use a protocol compiler, maybe a protobuf, to generate some stub code, and then you link the stub code with your application. So then you can write an RPC client and an RPC server, and the client can call functions on the RPC server. This architecture is invented in 1980s in this classic paper called Implementing Remote Procedure Call, and it is used. This architecture is used by a lot of open source RPC systems like gRPC, Thrift, and other RPC systems. Now the problem is if you use this kind of RPC libraries with a sidecar proxy in a service mesh setting, it incurs a lot of overheads, as already pointed out by prior papers. The key problem is it incurs a lot of marshalling and demarshalling overhead. So on the client side, you need to marshal the request into some buffer, and then the sidecar basically need to implement certain policy, and it has to marshal the message back into its original format, for example, HTTP or RPC, and then maybe you need to modify some part of it, you need to marshal it again. And on the receiver side, you also need to do a marshalling, apply some policy, then marshalling, and then deliver it to the RPC server. And on the way back, you also need to do this kind of marshalling and unmarshalling. Now, using this kind of traditional RPC library, it is very problematic to work with the sidecar because of in the following ways. First, the RPC library and the sidecar are weakly decoupled. Weakly coupled, this means it prevents us from doing some cross-layer optimization, and it operates at the layer 7. The second thing is the RPC library and the application are strongly coupled. So this is difficult to just upgrade the RPC library without shutting down the application itself. For example, if you find certain bug on the gRPC library, you want to upgrade the gRPC library, it means you need to shut down the process that is using the old version of the gRPC library. So what our design goal is, we want to operate at the layer 7, which means the sidecar and the client, they communicate on layer 7. This will reduce the marshalling and unmarshalling overhead. And we want to provide a weak coupling between the application code and the RPC implementation. This means we can upgrade the RPC implementation without shutting down the application itself. So here is the traditional RPC library with a sidecar, and here is our new design of mRPC. Yeah, mRPC, we only need to marshal once on the client side in the mRPC service. So mRPC service is a shared system service running on the machine, and many different clients talk to the same mRPC service. And on the receiver side, it only needs to do one marshalling, and so this have improved the data plane efficiency by quite a lot. So of course, there are many research challenges associated with having this design, because this design is fundamentally different from the 1980 design of the implementing RPC. Because of time limit, I just want to cover one design novelty. It is how to support a new application with different RPC specifications at runtime. We call this technique dynamic binding. So in order to talk about the dynamic binding, let's first think about what is static binding. So the RPC libraries currently use static binding. You provide your proto file, it generates some stop code, and you link with the application. And after that, you cannot modify the stop code anymore. And the problem is the new applications, each application will have its own different proto file. And this means in our, here, the marshalling code and the unmarshaled code and the stop code, they are combined in the same library, they are linked to the application. Where in mRPC, because the marshalling and unmarshalling has to be done on a shared system service, we have to decouple this stop code. So given a proto file, we want to generate some stuff for the application to use, but we want to have the separate part, the marshalling and unmarshalling part, which is decoupled from the stub, and it is injected into the mRPC system service side. So in this way, the application and the mRPC service can talk using layer 7 communication, and then the RPC service can apply policy and then use marshalling procedure to generate some TCP packet or RDMA message and send delivery to the remote site. So it reduces the marshalling and the unmarshalling overhead. So in mRPC, marshalling and unmarshalling code are decoupled from the user stuff and generated and dynamic loaded by the mRPC service instead. So we have certain evaluation. First is a large RPC grouplet. So this is comparing with the gRPC and gRPC plus Envoy. And we can enable like a similar set of network policy as Envoy, and we have seen 3.1x speed up on TCP transport. We can also compare with state-of-the-art low latency RPC library like eRPC, which is an RPC library on top of RDMA. And if we just compare the raw latency, we're slightly higher than eRPC, but if we need to have a proxy to, for example, control the RPC's traffic, you can think about this like a sidecar. We are showing a speed up of 1.7x if we have a similar sidecar for a RDMA-based RPC protocol. So this is another comparison. So we would like to implement a policy like filter RPCs based on some string in its RPC argument. In gRPC, if you want some policy, for example, you enable Envoy and you want to have this policy, the RPC rate drops from 50 to 13. But in mRPC, this only have 6% overhead because we only need to implement add a few lines of code in the mRPC service. So we also do end-to-end evaluation for the Death Star benchmark, and the Death Star benchmark is using gRPC Go. We ported to Rust version of gRPC because we currently only support a Rust front end. And using mRPC, we can speed up this Death Star bench workload by 2.5x. So in summary, we believe that this traditional RPC as a library approach, it is very hard to achieve manageability and efficiency at the same time. And we have built this new RPC system called mRPC. It is RPC as a managed system service. So it has a certain very interesting feature. I presented the efficient policy enforcement. It also have a very important feature that it can do upgrade of the RPC implementation without shutting down user applications. And it work with both TCP and RDMA. And our code is already open source. So if you're interested, please check it out. Thank you very much. And I'm happy to answer questions.
Yeah, Danyang, there's a question in the chat. I know, Mark, if you wanted to go ask your question directly.
Yeah, sure. Sorry. So maybe I should just raise my hand. I didn't want to interrupt. So I guess I'm a little confused. How is the communication between the application and the mRPC server working? Is that happening at? How does that work?
Yeah. So we use shared memory. So we basically implement a very lightweight shim RPC library that is linked with the application, but it does not have serialization and it does not have marshalling and marshalling in it.
So if it doesn't do any serialization, doesn't that imply that the mRPC server and the application both have to be written in, presumably, like presumably they're using like native data structures in whatever language they're written in. So presumably they have to be written in the same language in order for that shared memory to be useful.
So currently our prototype is using Rust. So both the application and the mRPC services using Rust. But we can also think about a language independent format between application and mRPC. So this will enable application to be written in different language, where mRPC is always written in Rust. So if you think about, let's say, but we don't need the marshalling to be like a marshal to TCP/IP packets. We can the RPC's argument can be scattered, have scattered memory addresses in the virtual address space, right, inside the application memory, right? So there's no explicit copy, because our mRPC also support RDMA backend. Yeah,
I see. So, but I mean, so there's, I mean, once you introduce that language agnostic format for communication, there's going to be some marshalling there, right? Like getting it into that format from whatever, however that differs from the way the language is natively implementing it. There'll be some equivalent of marshalling that has to happen there, right?
You are right, but I think we can just I don't think that's as heavyweight as today's marshalling. Like, for example, if you use gRPC today, it is the protobuf plus HTTP marshalling, right? And we just need to have some language independent types to be so that both the application and mRPC service can recognize this language independent type. I don't think that overhead is very large. Think about it, for example, Python and the C, right? The C sound, the C Python thing, right? This conversion, usually the overhead is not that high at all.
Sure. Okay.
So the high level goal is that we don't generate a TCP/IP packet from the application. We don't generate an RDMA packet from the application, right? They are not communicating through socket.
Understood.
Yeah.
So slightly unrelated question. So when you're comparing this to something like proxyless gRPC, it
right.
seems like the main advantage there, because proxyless gRPC, you don't have to use the sidecar in the first place, right? So it seems like the main advantage here is the ability to upgrade the RPC library independently of upgrading the application. Is that am I understanding correctly?
So I think there were three. I think there were several benefits. Let me list them. I feel there were several key benefits. First of all, if you do gRPC proxyless, you need to implement that service mesh functionality in every language gRPC library is written in, maybe 4 or 5 languages. So you have to make sure the version is consistent. Because if you upgrade the C++ core, but you didn't upgrade something else, it's hard to communicate between both ends. So this is number one. Our mRPC service only implementing Rust, no second language, right? The second is we are not binded into a particular transport like TCP, IP, or RDMA, because we can use RDMA as a backend, and our interface to application is really transport agnostic. Third is we can upgrade the RPC implementation or even any policy implementation dynamically, because we're running in a separate process. I feel these three are the most important benefits.